All right, let's get started with the review. So exam number 2 is going to be separated into 3 parts. There's going to be 3 main parts for the exam. The first part of the exam is going to talk about direct methods. So direct methods, and this one, direct method, is for solving a linear system of equations. Then we're going to have the second part. The second part is going to be about linear system of equation, but we're going to be using indirect methods. So indirect methods, and these are also known, this is what we often refer to as iterative methods. So methods that you use for solving things, implementing certain algorithms and routines. And then the last one, we're going to have number 3, which this one is what we refer to as nonlinear. So this one will be the nonlinear system of equations. And the difference between, as the name implies, the difference between the number 3 and number 2 and number 1 is you use number 1 and number 2 for dealing with linear system of equations. So that's something that we can represent as a matrix. We can represent, so both of these guys, we can represent them as A times X equals to B. But nonlinear system of equations, they cannot be represented as matrices, and that's why we use a different approach when we get to that point. So direct methods, you can think of them as, for example, using Gauss elimination. So Gauss elimination is the perfect example. There is also what we know as LU decomposition, and I'm just going to write it as LU decomp. Gauss elimination, LU decomposition, I think those are the main two direct methods that we see in this class. Maybe we see 1 or 2 more, but I can recall right now. Those are at least the ones that I think are prevalent to the exam. And then indirect methods, we have the Jacobi. We have the Jacobi iterative method, and then we have the Gauss-Seidel, which is the one that we saw in the project. So again, we have direct methods, we have indirect methods. Both of these guys, these two, this one and this one, they are for linear system of equations, for linear systems of equations. And then the last one is going to be nonlinear system of equation, which in this one we will use, just like in the previous project, sorry about that, we're going to use Newton-Raphson. And Newton-Raphson, in this case, it's very similar. It's very similar to what we saw in the first project, and I think it was on the second project that we used Newton-Raphson. But now we're gonna change it and we're gonna adapt it so that we can use it on a system of equation. Because before we saw it for only one equation. So again, I'm gonna talk on each of the 3 major points. And I'm going to try to give you guys like what kind of conceptual questions, what kind of concepts to know, what kind of things to go over, or what to expect as part of the material that we cover. So let me close this in here. It was a horrible line, but whatever. So the first thing that we're going to talk about is we're going to talk about direct methods. So we have direct methods, and these are methods that are given in this form. So we have an A square matrix multiply times an X solution vector, and then we have it equal to a B right hand side vector. So that is the system that we can kind of like set up when we're talking about direct method. When we're talking about linear system of equations, we have this system where we have A square matrix times X solution vectors equal to B right hand side vector. And there are a couple of things that we, as far as concepts go, there are a couple of things that we want to know about this, and one of them is there is the definition of something. So if I were to say something like this, if I were to tell you, okay, if I give you the actual value of matrix A, and so that either I give you or you calculate, you should be able to calculate this, you should be able to calculate the inverse of the matrix A. So if I give you matrix A and I give you the inverse of that matrix A, or I ask you to calculate the inverse of the matrix A, you should be able to calculate something called the conditioning number. I can say then the conditioning. So there is something called the condition number, And the way that we define the conditioning number is I can say K of A, where again, A is the matrix, A is the square matrix. I can say the conditioning number of A is equal to the multiplication between A. So A multiply times A inverse. And this, when you put the two bars on the side, that what that means is the norm. So this is kind of like just the form. One thing that you're gonna notice a lot, especially if you go through notes or if you read the textbook and things like that, it's whenever we're talking about a norm, we use this definition. We close something in between the bars, in between this sort of like absolute values. And the reason we do this is because we're talking about the norm of something. We're talking about the magnitude of something. And you don't necessarily have to specify what type of norm. In this class, you guys see a lot of norms, the different versions of the norms. You see L2 norm, L infinity, and all those different forms of norms. But we don't have to necessarily represent them when we're talking about them. We can just say norm, and the user is able to kind of like define what norm did they want to implement. Of course, for the purposes of this class, to keep it all consistent, and also for all of us to be on the same page, we tend to implement more than often. We tend to implement the infinity norm. That's what we very often implement. So if I say something like this, then where I can say where A. So if I tell you something like this, you can just assume that I'm talking about the infinity norm. And this is how I will write the infinity norm. And I know that the infinity norm for a matrix is, I'm going to give you the kind of like the raw definition of it. So in between I and M, where M is the dimension of the matrix, I have the sum from J equals 1 to M of the absolute value of the component of the IJ component. So what this pretty much mean, if you have a difficult time understanding the definition, if I have something like this, let's say I have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and this might not be the best example, but if I want to find like the infinity norm of that matrix, what I'm gonna do is I'm gonna look at the first row and I'm gonna add all of the components. So all of the components, all of my values, I'm gonna make them positive. I'm gonna make them absolute value. So if I have anything that is negative, I'm gonna make it an absolute value, and I'm gonna add each of the rows. So 1 plus 2 plus 3, that's gonna give me 6. 4 plus 5 plus 6, that will be what, 15, I think. I think that should be 15. And then 8, 9, and 7. I don't know what that is, so I'm going to use a calculator because I'm just lazy. 7 plus 8 plus 9. And that's going to be 24. So that's kind of like how you go. If you want to take the infinity norm of a matrix, if you have a square matrix, this is how you do it. You kind of like turn it into a vector, and then the vector, you're gonna do the same thing. How you take the infinity norm of a vector, you look through all the numbers, all of them are positive. You pick the one with the highest magnitude. So in this case, my answer will be 24 if I'm taking the infinity norm of this matrix. So that's what this routine right here, or this equation right here, represents. You take your matrix, you're gonna make them all positive, add the rows, so you turn it into a vector, and then you pick the highest value. So back to the conditioning number. So if you have a conditioning number, you know that you're gonna require to find the norm of the matrix A, and then that matrix A, you're also going to turn it into an inverse. So you're going to find the inverse of that. You will multiply the norms. So that's what it's important here. You're not multiplying the matrices, you're multiplying the norms of the matrix. For example, the infinity norm, if I wanted to find the conditioning number of A, it could be the infinity norm of A multiply times the infinity norm of the inverse of A. So these are two different matrices. And I want you to find the norm for A and the norm for the infinity A, which this one is going to be a coefficient, this one is going to be a coefficient, so it will be a number times a number, and that will give you your conditioning number. What is important about the conditioning number, first of all, it's important for you to be able to calculate it, but what it represents. What is the whole point of saying the conditioning number of A equals whatever number? Like, what is the point of that? And the idea is that if you have, so if K of A is small, So if my conditioning number of my matrix is small, then I can say that the system, when I say system, I mean the matrix A. So the system A is what is known as well conditioning. So it's well conditioning. If Ka, so if the conditioning number is big, if it's not small but on the contrary is big, we can say that the system is ill conditioned. That's very important that you understand the difference between those two. So again, we've calculated the conditioning number. The only thing that we need to calculate the conditioning number is the matrix A, and the matrix A will be given. However, you should be able to either find the inverse of matrix A. Matrix A could be a 2 by 2 or it could be a 3 by 3. It has to be a square matrix. And we will either give you the matrix A, we will give you the matrix A, and we will either give you the inverse of the matrix A, or we will ask you to calculate it. And you will use this equation right here, this one, the conditioning number equation, to calculate the conditioning number. And we will ask you most of the time, if you want to play it safe, use the infinity norm. If there is anything, if we want you to use a different type of norm, we will specify it on the question. But if it's not specified, always use the infinity norm. It's just the one that tends to make the most sense for the sake of the application that we're working on. But again, the conditioning number, the equation for the conditioning number is right here. Once you calculate the conditioning number, there could be a question that asks you what the conditioning number is, and then there could be another question that asks you what does it represent. Like, is the system well conditioned? Is the system ill conditioned? Like, what does it tell us about the system? So let me scroll down a little bit. I already talked about that. It's another thing that it's very important. Conditioning number is often combined with residuals, and it's one of those things that it has the ability of indicating if we're going to obtain the small residuals. However, I will not delve too much into that. I will say that a small residuals, so you can say that a system is well conditioned, and in addition, I can add this. I say in addition. And I don't think that's how you write in addition, but anyway. So in addition to that, I can say that small residuals. So I can say that small residuals will indicate an accurate solution. And usually these two go well together. Like if a system is well conditioned, if my conditioning number is small, my system will be deemed as well conditioned, and if my system is well conditioned, then the residuals that are produced are going to be small as the iteration converges, or as the system. Well, this if you're talking about direct method, I will just say that the residuals are going to be small. Like once you find your solutions, the residual for your solutions will be small. That's what tends to happen with small conditioning number. Another thing that it's important to know, so again, conditioning number is important. The relationship between residuals and conditioning number is important. It's also very important to understand when do we have to use, so this could be another question, when to use partial pivoting. So in this class, we particularly see partial pivoting rather than full pivoting, and this I is supposed to go here. Let me squeeze it to the right. So we have partial pivoting and we have full pivoting, and what is important for the class is to know whether it is necessary or not. And the way to kind of like know if we need to implement partial pivoting or full pivoting, it's whether our system. So if we have to look at A, and we have to ask, okay, I'm looking at my matrix A. Is matrix A is diagonally? So is A diagonally dominant? So you have to make sure that you know how to check if matrix A is diagonally dominant, and then if matrix A is not diagonally dominant, then you have to make it diagonally dominant, and the way that you do this is by implementing a partial pivoting algorithm or partial pivoting routine into your code. So diagonally dominancy, again, the whole idea of diagonally dominancy is that you can it guarantees that your solution, that you will converge as for a solution. It's very important when you're talking about iterative methods. For direct methods, it's more of like informational. So if it's diagonally dominant, you have to check if we check if it's necessary. Let's put it that way for when we're talking about direct methods. So in this kind of questions, like in this kind of section of the exam, we will ask you whether it is necessary or not to implement any form of partial or full pivoting. And you can tell me the answer by checking whether matrix A is diagonally dominant or not. If it's diagonally dominant, okay, cool. Tell me how that affects the system, how that affects the implementation or partial pivoting or not. And if it's not diagonally dominant, then okay, can you tell me why will we have to or not have to implement any form of pivoting? So it's very important that you understand the idea of partial pivoting. Once we move into, so that's kind of like conceptual. I will say all of this stuff that I just talked about implementing direct methods, because direct method is not a method in a specific, it's more of like a direct way of approaching something and finding an exact solution. So there is a difference between direct methods and indirect methods. Indirect methods are what we call exact methods, which yield exact solutions. And again, we talk about the conditioning number and what the conditioning number represents. What can it tell us about the system? We say that every time they ask us for a norm of something, like in this equation up here, we always default to the infinity norm, just for the purposes of this class. And unless it's specified, or unless they ask us to find a different type of norm. And in addition, it's important to know that small residuals, if your conditioning number is small and you can say that your system is well conditioned, which is going to yield small residuals. And a small residuals, which means that we have an accurate solution. So it's also important to know when to use partial pivoting, and the way we answer if we have to use partial pivoting or not is by looking at matrix A again, or system, that's what we call it, or system, and deciding whether it is diagonally dominant or not based on the diagonally dominant check. So I am gonna go ahead and move to the next part of the direct method. So the direct method, whenever you're working out, like there's always a combination of conceptual questions and workout problems. And for the workout problem, we're gonna be primarily interested in Gauss elimination. So Gauss elimination is what we're gonna be looking at for the direct method portion. There may be questions about LU decomposition. LU decomposition is a direct method. However, from my experience, you guys are never required to perform any sort of LU decomposition by hand. It's a long and tedious process, and it's very specific, the circumstances where it's applied. So, but it's important that you guys know about LU decomposition, but you're not gonna be, for the extent of my knowledge, you're not gonna be asked to perform any sort of like LU decomposition and solve the system using LU decomposition. As far as direct methods go, it will always most likely be Gauss elimination. So Gauss elimination, again, you're gonna be given a system in this form where A is a square matrix, X is the solution vector, and then B is the right-hand side vector. And then if we want you to solve this, Gauss elimination problem, you will be given the A square matrix, and you will be given the B right-hand side vector. So there are two ways you can solve this. And because we're talking about direct methods, it's always important to remember that you can always check your solution by doing A inverse. So you can do A inverse multiply times B, and that will give you your solution, because we're not talking about iterative method, we're talking about direct methods. But however, this is a good way of like checking your work. But that is not the main, that's like 1 out of 4 questions, I will say, because the main goal of this will be, we want you to carry out the Gauss elimination. I'm gonna call it GE. So we want you to carry out the Gauss elimination. Most likely, most of the time, I will say, if not always, with no pivoting. No pivoting is going to be necessary, because we know that the matrix that we're giving you will converge. And what we want is, we want you to triangulate the system. So make it into the upper triangular form. So upper triangular form. And once you have it in the upper triangular form, you have to solve it using back substitution. So back substitution, you're gonna start with your system, you're gonna put it in the upper triangular form, and then you're gonna solve it using back substitution. Now the important thing here, and if you don't know how to do Gauss elimination, how to do the whole upper triangular form and then doing back substitution, you can just Google it. Go to YouTube and watch a video. I think Patrick GMT has a video on Gauss elimination, and it's very clear, it's very straight to the point, and he shows you how to do the process. But it's important that you know how to construct the matrix A. So the matrix A that is triangular, I'm just going to put here tri. So the matrix A that is triangular, so the one that you obtain after you have triangulated your matrix, anything that you do to the left side of the equation, so everything that you do to the left is going to affect B. So you will also have a B triangulated vector. So once you finish your triangulation and your matrix A is in the upper triangular form and your vector B is in your vector B changes as your matrix A changes. So these two guys, we can ask you for a component of it. So I can ask you, okay, can you tell me what the component 2, 3 is, for example, of that matrix? Can you tell me that component? Or I can say, can you tell me the component from the vector B? Can you tell me the second component? So the kind of questions that you're going to have, and that's why it's important that you learn you get familiar with the whole process, because once you have your upper triangulated matrix, we can ask you for a particular component of the upper triangulated matrix A or a component for the upper triangulated matrix vector B. And then, of course, we will ask you for the solution vector. The solution vector, once you go and do back substitution, you start from the bottom going up. So the idea is that you are going to have, when you do upper triangulation, you're going to have a vector that looks like this. You're going to have a matrix that looks like this. You have coefficient all across this triangle, and you have a bunch of zeros here. You are going to have 0, 0, 0, 0. You're going to have a bunch of zeros in the lower triangular and a bunch of coefficients in the upper triangular. So let's say I have x1, x2, x3, and these ones are a1, a2, and a3, and a are coefficients. So I can start from the bottom. I'm going to start from the bottom, and then I'm going to move up. Why? Because here I can easily say this coefficient right here, like let's say that's whatever number times x3 is going to be equal to a3. So then I solve for x3, and I used it in the following equations moving up. So that's why we use back substitution that's why we put it in that form, so that we can just solve from the bottom up. Now, it's good if you can practice how to do it the other way, how you can do. So I'm going to put a star here, and I'm going to say also do lower triangular, because it could change. There could be a version of the exam, or there could be a different question that says also do lower triangular form, and there you will solve what is known. I think it's called forward. I think it's called forward substitution. I don't think I'm writing this correctly, but hey, anyway. Also do lower triangular and then forward substitution. So if you do it in upper triangular, you will solve using back substitution. If you do it in lower triangular, you will use forward substitution, which means, imagine the triangle, instead of being here, it's like flip. It's the other way around. So you will start from the bottom and move down. You will be specified on the exam if we want you guys to use upper triangular, if we want you guys to use lower triangular. But yeah, that's as far as Gauss elimination. So definitely watch a video on Gauss elimination. There are a lot of videos on Gauss elimination. Make sure you nail down how to put it in the upper triangular form or lower triangular form. It will be a good idea that you watch both. Make sure you understand what the components mean. Like if I tell you something like I, j for matrix A, the I is the rows, the J is the column. So if I tell you something like 2, 3, that means second row, third column. And you have to make sure you know how to extract those components, how to read it and pick the component that is the correct one. So again, be organized, have your upper triangulated matrix, your original matrix, your open triangulated matrix, and then everything that it's all your triangulated matrices and vectors. Make sure you have them, because we can ask you for a component of those. If you're asked to calculate the residual The formula of the residual, it's different. The formula that what you've seen before with the other methods that we saw. So for linear system of equation, the residual, it's going to be the matrix A times the solution vector X minus the solution vector B. Now you can also do it the other way around. You can do B minus AX, but this is normally the form that I do. And the only reason why we will ask you to find the residual is because we want you to find the infinity norm of the residual. So you have your residual, you can also calculate the infinity norm of the residual, and that will be the way that you look at this is when you do this, when you do a matrix times a vector minus a vector, so residual is supposed to be a vector. So what I'm going to do is I'm going to look at my residual vector. I am going to look at all of the values. So for example, if I have -1, I have 2, and I have -3. If I do the infinity norm of this, usually for vectors, we only put 1 bar, kind of like an absolute value. And some textbooks, you're going to see them using 2 bars like a norm. Some textbooks use the 2 bars for everything. Some textbooks use 2 bars like what we had before, only for vectors, some of them only for matrices. But every time you see something and you know it's a vector, don't think about an absolute value. You have to start thinking if n-dimensional system that have multiple dimensions, every time you see an absolute value, it doesn't mean the absolute value of a vector is a norm. That's I will say that's the definition. So what I'm going to do if I'm taking the infinity norm of this is I'm going to look at all the values. I'm going to make them all positive. So I'm going to take the absolute value of all of them. And I'm going to pick the largest one in magnitude. So the one with the highest magnitude will be 3. So the infinity norm in this case will be 3. So that's what we want you to do. And I did a whole discussion, I think during my lab, about why do we want to take infinity norm? Why is this relevant to us? Why is this important? And if you want to see me during office hours, I'll be more than happy to explain. And I just don't want to repeat it and make the review longer than it is supposed to be. It's not supposed to be super long, so I don't want to stretch it too far. But yeah, if you have your residual, if we ever ask you to calculate anything about residual, we will most likely not ask you for the vector itself, but the infinity norm. And remember, I showed you before how to calculate the infinity norm for a matrix. This one is for a vector, so you should be good to go with that aspect, or with respect to that. So again, just like we saw before, you have the conditioning number, and in this case, in this situation, you know the residual, so we know the actual value of the residual. And if you find the inverse of matrix A, you can calculate the inverse. If you find the inverse of matrix A, you can calculate the conditioning number. And if you have the conditioning number, and if you have the residual, if you have the actual residual vector, then you can talk about the system, just like we did before. Is the system well conditioned? Is the system ill conditioned? If it's ill conditioned, is it yielding a small residual? If it's well conditioned, is it yielding a small residual, so that we can say that we have accurate solutions at the end? So very conceptual. Again, it's very important that you know that. And the last thing, or not the last thing, but one of the things that is very important to recall from matrices, and this is something that you learned a long time ago, whether you can solve a system or not, if we can ask you, hey, is this something that you can solve? Is this something that can we achieve a solution or something like that? Before you even check if it's diagonally dominant, if the conditioning number is big or small, or like all those different techniques, always go back to the basics. Check if the determinant of matrix A, it's equal to 0. Why? Because if it's equal to 0, then you cannot solve the system. If it's equal to 0, you cannot solve the system. If it's equal to 0, you cannot find the inverse of the system because you're dividing by 0. So this is extremely important. Always check if the determinant of your matrix is equal to 0. If the determinant is equal to 0 of your matrix, then you cannot solve it. So if a question asks you like, hey, given this system, like, can you solve it? What can you say about the system? Check the determinant. If the determinant is equal to 0, say, nope, I cannot solve it, and then just move on. That's enough. That's a sufficient explanation when it comes to that. So now I'm going to talk about iterative methods solving linear. So how to solve the linear system of equation, but we're going to use iterative methods. So before I talk about direct methods, now iterative methods. Now we're going to talk about iterative method, and this is kind of like when when it gets more fun, I will say. So again, we're gonna consider a system. So I'm gonna consider a system given in this form: A x equals to b. So I have the same 4 that I have before, and just as we mentioned before, all the things that we talked about before, they still apply. All the things that we saw, we still have to check for them. Check if it's diagonally dominant. Check the conditioning number. Check if the determinant is equal to 0, because again, the diagonally dominant is very important in this case, because if our matrix is diagonally dominant, we have guarantee that it will converge. So it's very important that you check that. Always check if the determinant is equal to 0, because that will tell you whether you can even try to solve it at all. Because you can try to solve a matrix that is not diagonally dominant. However, your solution could explode. Like your routine there's no guarantee that it will converge. If your determinant is equal to 0, you know by a fact that it will not have a solution. It's just a mathematical terminology. But always check if it's diagonally dominant. If it's diagonally dominant, then yes, I know that I can come up with a solution. I know that the iterative method that I implement to my system will converge to a solution. So something that is very important, a question that I think without getting into too much detail, and if you are working on a part of Gauss-Seidel, for example, so if I have Gauss-Seidel, and for Gauss-Seidel, if they give me something called the theoretical iterative matrix, so theoretical, if they give you something like the theoretical iterative, if you have the theoretical iterative matrix, and for that theoretical iterative matrix, they calculate the eigenvalues. So the eigenvalues are calculated from that theoretical iterative matrix. What can you tell me about that? So what information can you tell me for that theoretical iterative matrix? And the whole idea of, if you're given, again, I don't want to get into too much detail, because you're not going to have to do this by hand. And it's going to be more of like, hey, this is the theoretical iterative matrix. The theoretical iterative matrix, the eigenvalues of that matrix are this. You may be asked to find those eigenvalues. I don't think you will be asked to find the theoretical iterative matrix. You find it with the whole process of LU decomposition. With the separating into lower, upper, and diagonal. But you may be, most likely, you will be given the matrix, the theoretical iterative matrix, and you may be asked to calculate for the eigenvalues of that matrix, which again is just normal eigenvalue calculations for a 2x2 or a 3x3. You should know how to calculate eigenvalues. But once you find those eigenvalues, what can you tell about those things? And what is important is to check that the magnitude, you have to check that the magnitude of all eigenvalues, you have to check that they're all less than 1. So make sure that when you check the eigenvalues, make sure that all of the magnitude of all of the eigenvalues that you find, all of them. So if you have a 3x3 system, you're going to have 3 eigenvalues. And they could have a real and imaginary part. You know how to find the magnitude of an imaginary number. You have to do this the square of the sum of the squares. And you want to check that the magnitude of all of those eigenvalues are less than 1. If the magnitude of all of those eigenvalues are less than 1, then you can expect your system to converge for when you're implementing Gauss-Seidel. If one of them is not less than 1, even if all of them are less than 1, if most of them are less than 1, but one of them is not less than 1, then you have no guarantee that your system is going to converge. So definitely always make sure when you're doing Gauss-Seidel and they give you a theoretical iterative matrix, and either they give you the eigenvalues or you calculate the eigenvalues, check that the magnitude of all of those eigenvalues are less than 1. And if they have real and imaginary parts, you have to calculate the magnitude of those numbers. So if you don't remember how to calculate the magnitude of a number that has a real and an imaginary part, make sure you check that. But as we saw before, if I give you an initial guess, and This is very important for iterative methods. So in direct methods, there are no such thing as an initial guess. For iterative methods, we always implement something like an initial guess. And before, an initial guess was given as a value. So when you were doing Newton-Raphson, when you were doing secant method or bisection, they were all given as a value. When we're doing iterative methods, we will give you the initial guess as a vector. And very often, we always put like it's not like a power, but we close it in parentheses. That's usually how with vectors, we indicate what number of the iteration we're in. Like when we're talking about Newton-Raphson, so if I say like Newton-Raphson or bisection or secant method, like we normally give you an x sub 0 for you to calculate x1, x2, x3. Like all of these guys were approximations of the same number. Like this is all same number. That's the same, it's the same root, I should say. These are all the same roots. However, for this type of guy, it's different because I can give you an n-dimensional vector, and the component of these vectors, the way that we call components is we call them x1, x2, and x3. So it can be confusing looking at what we were doing before and then switching to vectors, because now we're using the subscript as a way of describing the vector, the component of the vector, rather than the number of iterations. So that's why for the number of iteration, we put the number of the iteration as a parenthesis. So this one is what is called the initial. So this one is going to be my initial guess vector. And again, we indicate the initial portion by the number at the top that is closed in parentheses. So the only reason I'm telling you this is because if I give you an initial guess vector, you have your A matrix and you have your B vector, I can ask you to calculate the residual vector. So the residual vector, again, I have it's like this, it's a vector, but it has a number of iterations. So if I ask you to calculate the initial residual vector, you're gonna have your A matrix. Your matrix never changes, so A matrix always stays the same. And then I'm gonna have my X vector solution. My X vector solution, I will use the initial one. Why? Because I'm calculating the initial residual. It's very important that at this point you start getting the idea of, hey, the residual is a vector which changes at every single iteration. Why? Because it depends on an X solution vector, and the X solution vector changes on every single iteration. So I have AX minus B. Again, B is given, but B stays constant always. And this is how you will calculate. So if they give you an initial guess and they ask you to calculate your initial guess vector, this is how you will calculate your initial guess vector. You will plug in, the difference is you will use the X vector for that corresponding iteration. So if I ask you for your residual vector, for example, if I ask you for your residual vector at the second iteration, that will be the same A matrix, because A always stays the same. The only thing that changes is my X solution vector. I will use the X solution vector that I found at the second iteration, minus B. Right? So if I ask you for initial guess vector or for the initial residual, it uses the initial guess. If I ask you for the residual vector at the second iteration, you will use the approximation of the solution vector at the second iteration. And again, just like with everything, every time we're talking about a vector, we're talking about the residual of a vector, we are interested in finding the norm. So I can ask you for the norm infinity of the initial residual, or I can ask you for the norm infinity of the residual vector at the second iteration. Like I can ask you for something like that, and that's most likely what you will be asked, because we're interested in the largest and the value with the largest magnitude in your vectors, because if the largest value is going towards 0, then the whole vector is going towards 0 as the iteration increases. That's kind of like the whole idea. So I think I will talk more about this in a little bit, but I do want to say that just like we have with residual, something that you guys saw before is the iterative convergence. So iterative convergence, I'm going to put right here Newton-Raphson, so on R. And iterative convergence before was like the iterative convergence at the point K was the solution, this approximation. I should not use that K. I should, give me 1 second, because I'm talking about Newton-Raphson. So the iteration at K was the X at K minus dx at k minus 1. So it was and I believe it was the absolute value. So it was the absolute value of the current solution that we found, the current approximation of the root minus the previous approximation of the root. So this was just a value. This was just a number. This is a number, this is a number, and it yields a number. And that was how we did it before with Newton-Raphson, bisection, and Gauss and secant method. This case, it will be different because now if you take, before we had a value minus another value, an approximation of the root minus another approximation of the root. Now we're going to do the approximation of a solution vector minus the previous approximation of a solution vector. So if I am in the, let's say just for simplicity, if I'm in k plus 1, if I want to find the k plus 1, then this will be the x vector, my approximation of the vector at k plus 1 minus the previous approximation of the vector at k. So if I want to give you an example. If I'm asked to use, there is no such thing as initial iterative convergence, because if you're at the first, if you have the first initial solution, there is nothing for you to compare it to. So what I'm going to ask you to find, for example, is oops, that's a horrible bracket. I could ask you to find the iterative convergence at the first iteration. So I will put a 1 in here. So the iterative convergence at the first iteration will be your solution vector after one iteration minus your initial guess vector. Right? So it's the new solution minus the previous solution. That will be the iterative convergence at the first iteration. It's the solution of the first iteration minus the solution of the previous iteration. I guess all of these guys are vector. Why do I keep saying all of these guys are vectors? Because we're not interested in the vector. We're interested in, can you find the norm of that vector? Because that's what's really going to give us the insight of what's going on. If the largest value of that vector it's decreasing as the number, because again, this guy changes and this guy changes. Residual and iterative convergence, they're vectors. They don't stay the same. They change with every iterations. And again, just like in Newton-Raphson, bisection, and secant method, we're interested in seeing those decrease. We saw them going to 0 before. It's very difficult to tell whether a vector is going to 0 or not, unless you want to go through all of the components and check all of the components and make sure that they're decreasing with every iteration. So what we do is we check the magnitude of a vector. We check the infinity norm. The infinity norm tells you the magnitude of a vector. If the magnitude of a vector is decreasing with every iteration, that means I'm evaluating the magnitude of every new residual vector with every iteration. If that magnitude is going to 0, therefore I can say that my residual is going to 0. Same thing with iterative convergence. So it's very important that you make the shift from just thinking of normal values and start thinking into vectors. Vectors are definitely more powerful. But yeah, definitely keep that in mind. I do want to talk a little bit about the difference between Gauss-Seidel. So these are the two methods that you will be working them by hand, and you will be working like the whole process. What you guys can refer to as the workout problem. So there is Gauss-Seidel. There's Gauss-Seidel, and there is Jacobi. So the Jacobi method. So these are the two guys that you're going to be working on for linear system of equations for iterative method. And they both start the same. So assume that I have a system that looks like this. I have A11 plus X1. And this is kind of like where the matrix comes from. So again, these are coefficients. A are coefficients and X are my variables. X are my unknown. So 1, 3, X3, B1. And then I have A21. X1 plus A22, X2 plus A23. This takes forever to write, so just bear with me for a second. A31, X1, A32, X2 plus A33, X3, and this is going to be equal to B3. All right, so what I'm going to do now is I'm going to take each of the equations and I'm going to solve for one of the variables. So I'm going to take the first equation, I'm going to solve for X1, take the second equation, solve for X2, and take the third equation and solve for X3. So I'm just going to draw my arrows here so you can see what I'm doing. So I'm going to have X1 is going to be equal to B1 minus 1A2, and this is going to take me forever, so feel free to fast forward the video. There's no problem with that. There's no shame. A1, 1. B2, and I'm trying not to make a mistake as I go. 2, 1, x1, 2, 3, x3, divided by A2, 2. And then the last one, thank God, B3 minus A3, 1, x1 minus A3, 2, x2. And then divided by A3. So this right here, this is what we will use as our equation. So this is what I will use to find x1, this is what I will use to find x2, and this is what I will use to find x3. So those will be the three equations that I have and that I will use on my iterative process. So let me just scoot down a little. So you will either be given the matrix or you will be given the system. So if you're given a matrix, if you're given the system in a matrix form, remember that you can always turn your matrix into this form right here. You can always turn it into this, but just multiplying across. If you can multiply it across, and then after you multiply across, you can solve for each of them. That's one thing that you can do. You can also just know the form. And if you have a form like this, like if you have it like how I have it here on the side, you can always just take the components. Like if you know how to read the components, like first row, second column, first row, third column. Like if you know how to read the components of a matrix, you can just extract it and use this equation. You can use this equation right here and then just plug in the values. That will probably be the fastest thing. But again, you can always go from this form to a matrix form, or you can go the same follows backwards. Like you can go from a matrix form into the normal equation form and then solve for each of their components. So definitely pick your poison, pick what you think will help you the most. But you will be given, just like before, you will be given an initial guess vector. So you will give it an initial guess vector. And in this case, my system is a 3 by 3. So I have 3 unknowns. Therefore, I will have 1, 2, and 3, all my x's, and this will be my initial guess. So all of these guys are going to be actual values. They will not be variables. And I will be asked to find, you will be asked to find the solution vector. So the solution vector, and you will be asked to find the solution vector at whatever n, I should not use n because n is usually for size, but whatever k iteration. So that means we will find an x1, an x2, an x3 they will change with every iteration, but we're going to ask you for a particular iteration. So what is the solution vector after 2 iterations, after 3 iterations? And then in the same manner, we can also ask you to find the residual vector at a k iteration and the iterative convergence at a k iteration. So find those guys at a k iteration. Again, remember that these two guys, this one and this ones, they are vectors. And what I mean by they're vectors, it means we want the norm. So most of the time we want norms. And the norm that we want is more often the infinity one. So we want norms. For residual and iterative convergence, it makes sense to look at the norm. For the solution, it makes no sense to look at the norm. So don't worry about that. But I'm going to write the equations one more time. If I'm looking at the residual at a k iteration, then that will be matrix A times vector, that vector at the current iteration minus the v vector. So that's how you calculate your residual at every iteration. And then if you want to calculate the iterative convergence at a k iteration, it's always the solution at the k iteration minus, that looks more like an h, but it's a k, and then minus the solution at k minus 1. So what is important to think here is that, again, if this cannot be equal to 0. So in this particular case, k cannot be equal to 0 because there is no such thing as an initial iterative convergence. You start at 1 and you move on, because there is nothing. If you're at 0, there is no such thing as x minus 1. You cannot compare it to anything. Okay, so what is different? So there is a difference between Gauss-Seidel and Jacobi, and they both use the same process right here these ones that I have over here, that's to solve x1, x2, and x3. The difference will be in how they update themselves. Like what do we call the end of the iteration, or at what point do we implement the new values versus the old values? So I'm gonna give an example using Gauss-Seidel. So not much of a numerical example, but just so you see like the idea. So Gauss-Seidel is what we know as a self-updating algorithm, in the sense that it doesn't wait till the iteration is over to update the values that we're using. So for example, if I want to calculate x1 at the first iteration, so x1 at the first iteration, I'm gonna use this equation that I have up here, this one. So if I want to calculate x1 at the first iteration, I will use, again, b1 minus a12, that's exactly what I had before. I'm going to use x2 from the initial guess, again, because I'm calculating the first iteration. So I'm going to use the value from the initial guess. And then I'm going to have a13, x3 from the initial guess, and that's going to be divided by a11. So that will be the same for both of them. So this one, and if let's say I'm doing Jacobi here on the side, if I'm doing Jacobi will be the same thing, the first equation. The difference now is when I'm calculating x2. So if I'm calculating x2 for the first iteration, I am going to do b2 minus a21, and then in here, what I will write, it's what you will expect me to write is okay, I'm going to use x1 from the initial guess, because I haven't used it. I haven't used x1 from the initial guess. However, that's not what Jacobi wants me to do. I'm sorry, what Gauss-Seidel wants me to do. Gauss-Seidel wants me to use, and I wrote it again, Gauss-Seidel wants me to use the solution I just found. So this x that I just found, it wants me to use it because it's the most up-to-date. It wants me to use that one. So I never get to use the x1 from the initial guess, because in the first line I calculated for x1, and that's the one that it wants me to use. It wants me to use it as soon as I need it. So the definition of it, that's what I mean, but it's a self-updating algorithm, in the sense that as soon as I solve for something, I will use that approximation. I don't use the approximation from the previous iteration, be it the initial guess or whatever. As soon as I find something, that's what I'm gonna use. Now, everything else is the same. 2, 3, x3, and the x3, I haven't found x3. I don't have any new updated version of x3, so I'm going to use the one from the initial guess. And all of this gets divided by a22. Now x3, it's also going to change. I'm going to approximate x3 of my initial guess. So this is going to be b3 minus a31, and a31 is multiplied by x1, but again, I found x1, so I'm not going to use the one from the initial guess. And then I have a32 x2, and I found this guy. I found the approximation, the most up-to-date approximation of x2, so that's what I'm going to use here. I'm not going to use the one from the initial guess, because the one of the initial guess is considered outdated. And that's how, this is how I find x1, x2, and x3. So you see x1, it's not considered as up to date as the other two, but x2 and x3 are already like up to date. So that's why you update. So I can say you update whatever vector you're using for x as soon as found. So I'm going to say as soon as possible. So you use it as soon as you find. So if you find an approximation for x1, you use it right away in the calculation of x2 and x3. If you find an approximation of x2, you use it right away in the approximation of x3. So that will be the difference. And now you're going to see how different Jacobi is. So if I want to find Jacobi, if I want to find the first component of x, this is assuming I have a 3x3 system, which is, it's like at worst as you will get it in this class. And so assuming that I have Jacobi, I'm going to have b1 minus 1a2. It's going to be the same as the one on the left. I've used the one on the initial guess. 1, 3, x3, 0. And then this is divided by a11. Now x2, if I want to calculate the first iteration for the component x2, I'm going to have b2 minus a21, and then different than in Gauss-Seidel, this time I will use the x1. Even though I already found an x1, an approximation for x1, I'm not going to update it right away. I'm going to continue using the values from the previous iteration. So I wait till the end of the iteration of my current iteration for me to update all my values. I don't update them as I go, which is what you do when you're dealing with Gauss-Seidel. So again, x3, p3, a31, x1 from the initial guess, and then x32, x2 from the initial guess. So you don't use them, you don't update them, you continue using the same one. So now when I complete this whole process, when I do this new iteration, I will find my approximated values for x1, x2, and x3. And that's what I will call my new iteration. This will be all of these guys, all of these values, they're what I call my new iteration, x1. Right, so that's what I'm solving here. Same thing in here. All of those values that I found, all of this x1, x2, and x3, that's what I will call my x vector at the first iteration. But they won't be, there's two different processes of doing the same thing, but one of them is always trying to be up to date. It's always trying to be the most up to date combination, I should call it like that. But yeah, in this one, you update when it ends, update at the end of iteration. So you update your variables at the end of the iteration. You don't update it as it goes. I think very important before I move into the next part, the last portion of the review, is how do you calculate the number of flops? There is something called flops, and I'm gonna write it down here. I should probably clear my screen. Yeah, let me clear it, and let me go all the way to the top. Okay, there you go. So if you want to calculate something, there's something called flops, and flops is the floating point calculation. It's like how many calculations, how many subtraction, addition, subtraction, multiplication, division do you have to do to achieve a certain kind of, like, to converge, for you to complete like if you're doing Gauss elimination or anything like that. And the idea is, if you're doing a direct method, so if you're doing a direct method on an n by n system, so if you have a matrix A that is an n by n, the way that you calculate the number of floating point operations, that's what it's called, floating point operations, is you do n cube. So if the dimensions are n, so if you have like a 2 by 2 system, if you have a 2 by 2, you take 2 and you put it to the cube, and that tells you how many floating point operations do you have to do to converge to a solution. And if you're talking about an indirect method, so an indirect method, you will, in the same thing, it's an n by n. It's an n by n system. You will be given a k, where k is the number of iterations. So given a number of iterations, how many iterations to convergence, like how, if we know the number of iterations that it's going to take us to converge, how many floating point operations we have, that's going to be equal to k n times n. So it's the dimensions of the matrix multiplied times the number of iterations. That's for an indirect method, for something like Gauss-Seidel and Jacobi. For a direct method, we don't have iterations on direct method. If we just want to know how many floating point operations we're going to have to do, that's going to be n cubed. So the size of the matrix is the n. If it's an n by n matrix, it's going to be n cubed. So that's one thing that I think it's very important for you to know for the purposes of the exam. All right, the last thing. Let me just check the time, make sure that I'm okay. All right, I need to hurry up. But so the last thing will be nonlinear system of equations. And again, let me finish writing a nonlinear system of equations. We saw traditional system of, or I should not say traditional. We saw linear system of equations. That's why we do matrices. Linear system of equations, you can put them in a matrix form and you can solve them using Gauss-Seidel and Gauss elimination. These are nonlinear system of equations. So nonlinear system of equation will require us to do Newton-Raphson. So if you recall from Newton-Raphson, and I'm gonna keep calling NR, Newton-Raphson, the way that we found a new solution, or a new approximation of dx was xk plus 1 equals to xk minus the function evaluated at xk divided by the prime of xk. That's how we found and this was equal to a value. This was equal to a number. Now, instead of doing that, and this is kind of like where the notation is going to change, all x's are now vectors. X is a vector, x is a vector, and the function, it's a vector. When you evaluate the function, you obtain a vector. You cannot take a vector and divide it by another vector. So what we're going to do instead, when we're doing with system, I'm going to say here system of equation. When we're dealing with system of equation, what I'm going to do is I'm going to have a new solution vector. That's my new vector. My new solution vector k plus 1 is going to be equal, and it's going to be the same form, but it's going to change ever so slightly. It's going to be my previous vector minus, again, this I cannot do it because of laws of linear algebra, and I can get into details of that later if you're interested. But instead of doing that, what I'm going to say is I'm going to calculate the Jacobian, the inverse of the Jacobian at whatever k iteration, and I'm going to multiply that by the vector of my function. So my function evaluated at the vector at the current iteration. So this one, so this is a vector multiplied times the Jacobian, and the solution for this, it's going to be a vector. So this one, the solution of this is going to be the vector solution. Again, x to the k plus 1 is going to be a vector. And that's this whole idea here. We solve it by doing the inverse of the Jacobian multiplied times the function. Now, what it's important to know here is, number one, make sure that you know how to do matrices on your calculator, because you can do all of this in one go. You can do all this whole thing. If you define one matrix as if you define your vector as one of the, I think most scientific calculators can do up to like 3 matrices or something like that, or more. I think the maximum dimensions is 3 by 3. But you can do this vector minus the inverse of the Jacobian multiplied times the function evaluated at that point. And you can do all of that in one go using the calculator. Before, in this case, we will give in, as I mentioned before, you will give in an x sub naught that was a number. In this case, you're going to be given an x initial guess vector, just like I mentioned before. You will be given an x initial guess vector, and that's going to have like however many components, x1, x2. For example, if you're talking about only 2 equations, you will have x1 and x2. And one thing that is very important is that when you're dealing with nonlinear system of equations, again, this is the equation that you need for everything. If we ask you to find residual at a certain iteration or iterative convergence at a certain iteration, it follows the same idea as what you saw before. But it is very important that you understand, for example, the calculation of the Jacobian. If you want to calculate the Jacobian at a certain iteration, you will have to do derivative of the first function with respect to the first variable, derivative of the first function with respect to the second variable, derivative of the second function with respect to the first variable, derivative with the second function with respect to the second variable. So this for a 2 by 2. The rows is the function and the columns is the variable. So the first one is going to be, again, rows is the function. If I keep adding rows, that will be partials of a certain function. And if I keep adding columns, it's with respect to a certain variable. So, but this is for a particular k. When you find the Jacobian changes. The Jacobian will change with every single iteration as well. So make sure that when you find the Jacobian, you find it in terms of your unknown variables. Don't try to calculate the Jacobian every single time. Write it in terms of variables, like in terms of 2x1 plus x2, something like that. Like write it in terms of the unknown variables, because then whenever you're doing this process, every single time it's just a matter of plugging the values, plugging the approximation of the x's, and then you calculate the corresponding Jacobian for that portion, so that then you can calculate this equation right here. That's the easiest thing to do, rather than try to do this equation, because the plain Jacobian, like the Jacobian in terms of variables, it's not going to change. Jacobian always stays the same. What changes are the values. So that's why, because the x changes with every iteration, that's why your Jacobian changes with every iteration. But the shape of the Jacobian, like when you take these partials of functions, it will always stay the same. What changes is the evaluation, because you're evaluated at different values. And another thing to remember is the residual. So the residual, this is not a linear system of equation. So your residual is going to be the evaluation of your function at a certain x. So at the x at the particular iteration, that's what you're going to evaluate. So you're just going to you're going to take the function and you're going to evaluate it using the values of the vector. Your function will be that your residual is a vector again. And what this means is that we can find the norm of that vector. So at a certain k, we can find the infinity norm of that vector. And iterative convergence is the same thing. Iterative convergence is going to have the same form that I showed you before, where you're going to have k is equal to the solution at k minus the solution at k minus 1. And again, just like always, we can always ask you for calculating the norm of that value. Like anything that is a vector that is not a solution, we will most likely ask you for calculating the norm. So what can be different? What kind of questions can we ask you about this? Just like before, we can ask you for a particular residual, the residual norm of a particular iteration, the iterative convergence at a particular iteration, a component of the Jacobian at a particular iteration, or just a solution at a particular iteration, like either a component of the solution vector or the whole solution vector. We can ask you about that. So definitely make sure you're very systematic, very consistent, and very strategic when you're coming up with this system, because this equation is all you need. This one right here. The current vector, or the previous, if you want to calculate the next iteration, is the current iteration vector minus the Jacobian evaluated at the current iteration. That's why I say when you calculate the Jacobian, leave it plain. Don't plug in any x's. Leave it in terms of the variables. Multiply times the function evaluated at the variables. Like you can very well just write everything in terms of the variables and then just plug it in. Just change the value of x's. X's are the only things that change. So you can have your shape of your solution and then just plug in the x's and then solve like that. So definitely calculate Jacobian in terms of your x's. And yeah, so what things are going to change every single iteration? Your x is going to change every single iteration, of course, because your solution we're approximated a solution, but things that are dependent on x are going to change, such as the evaluation of the Jacobian. It changes with every iteration because Jacobian is dependent on the current x. And your function vector is also going to change. Why? Because your function is dependent on the x's. Your function, just like you have seen before, a function takes an input. The input in this case is a vector, is the vector of x's, so it will change at every single iteration. But yeah, that is everything that is going to be as part of the exam. If you have any questions or anything like that, just send me a message. And if there is anything that was that I didn't explain correctly, or if you have any further questions, just let me know. All right. Thank you.